Welcome to the course lecture on advanced control systems. I am Professor Somnath Majhi, Department of Electronics and Electrical Engineering, IIT Guwahati. I have been working in this department of EEE since 1999. Also, I have been teaching this course since last 2 years. This course, Advanced Control System, is an advanced level course, and prerequisite for this course is control systems engineering. So, prerequisite for this course is control systems engineering. Basics on control systems theory is required to fully understand the content of the lectures. Books for reference books for this course would be Advanced Control Theory, Relay Feedback Approach by S. Majhi, published by Cengage Asia and Cengage India Private Limited in the year 2009. Next reference book would be New Identifications and Design Methods, authored by A. Johnson and H. Moradi, published by Springer Verlag 2005. Next book would be Control Systems Engineering, a basic level book, authored by N. S. Nish and published by John Wiley and Sons in 2008. Now, to fully understand the basics of advanced control theory course, one need to know what a control theory is first. For that, we shall consider a simple fan speed control system. Given a fan as a system or process or plant as we are used to call, once it is subjected to certain input voltage, we do get some speed from the fan. That speed is known as actual speed or output of the plant. Often it is controlled and its speed can be controlled by a controller. Now, the controller output is designated by U. The controller, the basic job of a controller is to control the speed of the fan. That can be initiated with the help of the input voltages. When we apply different input voltages, different fan speeds result in. Now, what happens? I wish to have a constant or fixed fan speed. Suppose I wish to have 1500 RPM from the fan. For that, what one has to do? One need to put a controller in the loop and first sense the speed of the fan with the help of a speed sensor. The output of speed sensor will be known as Y, the measured speed, that is compared with the reference speed, that is known often as desired output, and the difference is fed to a controller. Then the controller acts in such a way that the speed of the fan becomes 1500 RPM exactly, provided there are no input fluctuations. So, this gives basically the structure of a very simple control system, closed loop control systems. How our course is different from basic control system theory? What is advanced in this control system theory? The fan dynamics. Unless we know properly the dynamics of a fan, it is very difficult to set the parameters of the controller, and unless the parameters of the controller are set accurately, it is not often expected to get desired output from the system. That means, the speed of the fan may not be 1500 RPM. For that, what happens? It is essential to find accurate model of a fan. That comes under identification. That will be included in this course lectures. How to model, how to properly identify the dynamics of a plant or fan in this case. Now, we shall see what are the basic building blocks of a control system. A control system basic building blocks are comprised of plant as shown over here, which is a fan as we have seen earlier, controller which can be made up of electronic components or one can have software programs for the same as well. Now, also a sensor which is one of the most important part of the control loop. So, plant, sensor, controller are the three basic components of the building blocks of a basic control system. Y A refers to the actual output of the system, whereas Y is known as the measured output. There could be differences between the two depending on the accuracy of the sensor. So, it is very essential to model and employ an accurate sensor for many control systems. Now, again coming to the basics of how it is advanced control, what about the advanced control theory? What is there? What should be the contents of an advanced control theory? Lecture 1 will deal with control configurations first, performance description of a control systems. What do we mean by control configurations? Control configurations means where to put the controller in the closed loop. It can be put in series with the plant or process, in tandem with, in parallel with, or in both way, in series feedback combination. That is known as controller configurations. Next comes the performance description of a control systems. These things we shall learn in lecture 1, where performance description of a control systems usually are given by time domain and frequency domain measures, that we shall study in lecture 2. So, lecture 2 will give the performance measures of a real time control systems in time and frequency domains. In time domain, there are certain things like time domain parameters as we are used to, as you are expected to have learned in basic control systems engineering course. Those are rise time, settling time, steady state error, decay ratio, overshoot, undershoot, peak time and so on. So, these fall under the time domain performance measures of a control system. Similarly, coming to the frequency domain performance measures, we have phase margins, gain margins, phase and gain crossover frequencies and so on. Now, these two are very important. Why? Unless we are happy with the performance measures, we need to change the dynamics of a controller. How the controller dynamics can be changed? With the help of typical type of controllers employed in industries and academia. One of the controllers which is quite often used in process industries is PID controller. Its full form is proportional integral derivative controller. In lecture 3, we shall study in detail what are different types of PID controller and its variants. Now, what are PID controllers? To know that, let us see one simple block diagram. A controller is subjected to error inputs, which is made up of the difference between the reference input and the measured output of a system. So, set point shown over here is nothing but the reference input, and plant output shown over here is the measured output. These are the two inputs to a controller. and the output from the controller is control output. As we have seen in the fan speed control system, unless the controller is there in the loop, it is very hard to get the desired 1500 RPM from the control system, from the fan speed control system. Now, what are those three components of a PID controller? This is the proportional controller we have, integral controller and derivative controllers all in parallel. This form of the PID controller is known as parallel PID controller. Now, you see there are some other parameters involved in the controller structure. Those are lambda 1 and lambda 2. Depending on various values of lambda 1 and lambda 2, we get the variants of PID controller. Variants means, now if I set lambda 1, lambda 2 equal to 1, I get PID parallel form controller. When lambda 1, lambda 2 becomes 0, I get only PI controller. Similarly, various combinations of lambda 1 and lambda 2 will give us variants of the PID controller. Now, why we have the PID controller in this typical form? The main reason is that we have got some important effects generated by a PID controller. Those are derivative kick and integral wind up. Those two actions are not desirable in real time systems. Therefore, we do have one derivative filter along with the derivative controller. Similarly, the integral controller has been put in such a way, if you look at this, then you can make out that basically the integral controller is available in the feedback path of a system, inner feedback path of a system, avoiding integral wind up action. So, to initiate anti-integral wind up actions, one has to have different type of controller configurations. So, all these things we shall study in lecture 3. Now, coming to the next lecture, the fourth one, which has got PID controller design for single input, single output processes. What are single input, single output processes? You are used to that. Mostly control systems engineering course at basic level deals with single input, single output processes. The process is subjected to one input and one output. So, we shall discuss in detail different simple methods available for design of PID controllers based on the model of dynamic model of SISO processes. Dynamic models of SISO processes can be obtained by various ways. All those things we shall discuss in subsequent lectures. Now, coming to lecture 5, which is about the design of PID controllers for 2 input, 2 output processes. How that is different from single input, single output process, that can be explained with the help of the block diagram given over here. So, this block diagram represents the control system for a 2 input, 2 output process. Now, this GS represents the 2 input, 2 output process or plant. So, if a plant is subjected to interactions from different internal loops, that type of process or plant is known as multivariable or 2 input, 2 output plant. These 2 input, 2 output plants can be extended to multivariable plants with the help of lots of interactions within the system. Now, for TITO systems, generally 2 PID controllers are used for getting satisfactory closed loop performance from the system. So, the 2 PID controllers can be designed provided the dynamics of the TITO process is known accurately. All those things can be discussed in lecture 5. After lecture 5, we shall have the next lecture on limitations of PID controllers. Here, what are the structural limitations of PID controllers, basic limitations of PID controllers, why do we have different type of PID controllers than the classical parallel or series form of PID controllers. All those things will be discussed in detail in lecture 6. We will show how PID is unable to perform well for some typical processes like unstable processes, integrating processes, processes possessing double integrators and so on, and what is to be done to overcome the limitations of PID controllers. Lecture 7 introduces another form of PID controller often known as PIPD controller, where the PI controller will be in series with the plant in the feed forward path, whereas PD controller will be in the feedback path. PIPD controller for SISO processes is very important in the sense that this control technique can be used for controlling a varieties of processes, a class of processes that can include stable, unstable and integrating processes. What a PIPD controller is? The PIPD controller can be depicted in this form. This block diagram represents a closed loop system where we have got a controller in the feed forward path and a controller in the feedback path. The job of this feedback controller is primarily to stabilize the process dynamics. This process could be stable, unstable or integrating. When it is unstable and integrating, unless its dynamics is stabilized or its closed loop poles are located at some proper locations, often it has been found that it is difficult to design a suitable controller, a feed forward controller that will meet design specifications. For that reason, there is the need for this PIPD controller, where we shall have a PI controller in the feed forward path and a PD controller in the feedback path. Now, GC1 can usually be PI or phase lag type. GC2 is generally of proportional derivative or proportional derivative type. These combinations make and give us PIPD control. So, the design of PIPD controller will be discussed in lecture 7, and we will also show how the PIPD controllers outperform the PID controllers for many SISO processes. The SISO processes shall include stable, unstable and integrating processes in our discussions. Lecture 8 is all about PIPD controllers designed for TITO processes. As we have seen, we can employ two PID controllers for TITO processes, but if two PIPD controllers can be employed in place of the PID controllers, then it is expected to get improved performances from the closed loop systems. Lecture 9 will introduce effects of measurement noise and load disturbances in closed loop control systems, and also we shall discuss about measures to deal with effects of measurement noise and load disturbances. Lecture 10 will be on relay control system for identification. What is identification of a system? Identification is meant by finding the dynamics of a plant or process with available information. Any plant or process is subjected to process input and output. Input and output can be collected, and the set of input output can give us information that can be used for finding the dynamic model of a process. That is known as identification. Relay control system for identification. Why relay? Why not any other mechanism for identification? It is one of the most simple nonlinear device that can be employed for identification of many systems. Now, what a relay control system is? Here, this block diagram shows a relay in autonomous closed loop. Relay is replacing a PID controller, and the job of the relay is to find the dynamics, to estimate the dynamic model of a plant. When the relay is put in the closed loop, the plant is expected to get output of this form. Look at the output carefully. The output of the plant when relay is in the loop becomes oscillatory. So, it gives a typical oscillatory output, a periodic output as well, which has got some peak amplitude given by A p, the peak amplitude given by A p, and the time period given by 2 tau. Now, the input to the plant at that times become either rectangular or square, and that is of this typical form. So, this relay, a symmetrical relay that can be shown as of this form, having amplitude h and minus h, gives us a typical output of the plant. So, this plant output and input information can be used to find the dynamic model of this plant. Why relay again? This relay is going to drive the plant action in such a way that its output becomes not only oscillatory, but becomes periodic and oscillatory. So, when the relay is symmetrical, we get some symmetrical output of this typical form, and using the information we can find the dynamic model of the plant. Now, these things will be studied in lecture 10. Now, why there is describing function for the relay? The relay can be approximately represented by some gain known as describing function. Different type of describing functions for nonlinear systems also will be discussed in this lecture. Lecture 11 will be on df of a relay, describing function of a relay, and we shall discuss what are critical gain, critical period of the output of a plant when relay is in the closed loop. And we shall also try to estimate process model parameters, assuming certain form of the process dynamics. A process dynamics can be assumed in the form of either first order plus delay transfer function form given as k e to the power minus theta s upon t 1 s plus 1, where theta represents the time delay of a process model, k is the steady state gain, t 1 is the time constant of the first order process model. Similarly, we can have a second order plus time delay model for the dynamics of stable, unstable and integrating plants, that can be given as k e to the power minus theta s t 1 s plus 1 s and t 2 s plus 1. So, this gives the transfer function model of a stable second order plus time delay plant. Now, when I put minus over here, I get an unstable second order transfer function model, and when we limit the values of T 2 to infinity, T 2 tends to infinity such that k upon T 2 tends to some finite value. In that case, we get a transfer function model that can be shown as k e to the power minus theta s s upon T 2 s plus 1, that gives us a model transfer function model for integrating second order plant. So, all these transfer function models can be realized from the basic second order plus time delay model. That is why it is known as the general second order plus time delay model for different type of plants. Lecture 12 will discuss about the offline and online identification. What are offline and online identifications? In the offline identification, the controller is replaced by relay and the parameters of dynamic model of the plants are estimated first. Then the controller parameters are tuned based on the acquired model. That is known as offline identification and tuning of controller. In the offline identification, the controller will be replaced by the relay, whereas in the online identification, the controller will always be in action, will be in the loop, and the relay will be connected in parallel with the controller. That gives us online identification schemes for different type of closed loop control systems. Now, again using the describing function method, we shall try to identify the parameters of a model based on offline identification scheme. Lecture 13 will be on online identification of stable, unstable and integrating plants, where the controller will always be in action along with relay at the time of identification, and once the identification process is over, then the relay will be taken out of the loop, thus giving us the normal operation of the closed loop system. Now, going to the next lecture, lecture 14 will be based on basically analytical expressions for online identification of stable, unstable and integrating plants. We shall assume some specified form of transfer function models and will try to estimate the unknown parameters of the models. So, analytical expressions will be based on describing function analysis. Next, Model parameter accuracy and sensitivity will be discussed in lecture 15. These two things are very important, whether our identification schemes are giving us desired results or not, that can be ascertained from the study of accuracy and sensitivity of the identification methods. Now, next lecture shall be on effects of static load and measurement noise disturbances during the identification tests. We shall make use of some simulation studies to see how our identification schemes are giving us results in the face of static load disturbances or low frequency noise disturbances and measurement noise disturbances known as high frequency disturbances. Now, to alleviate those problems, there are certain techniques. One can make use of Fourier series or wavelet based techniques to get rid of problems associated with the output of a plant, which is subjected to static load and measurement noise disturbances. All those things will be studied in lecture 16, and finally, in lecture 17 we shall have reviews of describing function based identification methods. Lecture 18 will be on time domain based identification, which shall make use of state space analysis techniques for identification, and accuracy in identification will be discussed as well using the technique of small value theorem. Now, lecture 19 will be analytical expressions for identification of stable, unstable and integrating plants. The analytical expressions will be based on the shape of the output, of the plant, which is subjected to a relay feedback. As we have seen earlier, the output will be mostly a symmetrical periodic output with certain peak amplitude and period. So, based on the peak amplitude and period, one can estimate the model parameters of stable, unstable and integrating plants. But based on the shape of the output, one can also derive a number of analytical expressions. Those expressions can be used further for estimation of the unknown plant model parameters. So, we shall make use of state space analysis to obtain the analytical expressions based on the shape of the output, oscillatory output from the plants. Next, we shall also derive a set of general analytical expressions that can be made use of for identifying stable, unstable and integrating plants. Why those are known as general analytical expressions? The analytical expressions need not be derived one each for stable or unstable or integrating plants, rather the same set of expressions with certain limiting values can be used to estimate the unknown parameters. Lecture 21 will be on special cases like a plant having multiplicity of a pole, which can be shown as k e to the power minus theta s T 1 s plus minus 1 to the power n. This is known as a plant model having multiplicity of poles, where n can assume various values starting from 2, 3 onwards. So, we shall have a few more special cases on this when n equal to 2, when n equal to 3, what should be the analytical expressions and how we can solve the set of analytical expressions using certain nonlinear equation solvers and find the unknowns of the plan model parameters, which are k, theta, t1 and n. Again we shall deal with another special case, a plan model with right half plane pole, which can again be shown as k minus t0 s plus 1 upon t1 s plus 1 to the power n. So, here this type of plan model is supposed to have model with right half plane poles. Next lecture will also deal with a special case, plant having complex conjugate poles. In this case, when the T1 and T2 we have been discussing so far, when they become complex or complex numbers, in that case the plant model are often given in the form of k e to the power minus theta s, a square plus b s plus 1 and so, where b is such that we get under damped action given or shown by this type of models. So, this is also falling under one special case, and we shall try to derive a set of analytical expressions for such cases. Next, we shall study estimation of date time parameter of a transfer function model. A second order transfer function model can have 3 to 4 unknowns. If some of the unknowns can be estimated by some other technique, then that will reduce the burden on us in estimating the number of unknowns. It has been found that some other simple techniques can be made use of to estimate some of the unknowns of the second order transfer function models. Date time parameter, which is often given as theta in our lectures, can be estimated by some other techniques considering the output, symmetrical output of the plant subjected to relay feedback, using some derivative of the output signal and so on, and zero crossings, we can easily find this unknown parameter of the model transfer functions. So, that will be discussed in lecture 24. Lecture 25 will be on exactness of identification in the face of measurement noise and static load disturbances. So, accuracy of identification can be studied in this lecture. Now, next lecture will be on time domain based offline and online identification. Now, offline identification of SISO plan models can be extended for TITO plan models, that we shall see in the lectures 27 and 28. Then we shall review the identification schemes based on state space or time domain before going to the next lecture, which is on model free controller design. After identification phase is over, we shall go to the controller design. Controllers can be designed by two ways, either model based or model free. In the model free controller design, plant information will be acquired online, and that information will be fed to the controller simultaneously when the controller is in action. That is known as model free controller design. And we shall see also automatic tuning of industrial controllers and their advantages and limitations in lecture 30. Lecture 31, 32 will discuss about the online tuning of controllers using frequency domain. In the frequency domain based controller tuning, phase and gain margins will be the two important parameters that are to be taken into account, and we shall try to design robust controller based on frequency domain. The next lecture, 33rd lecture will be on design of PD and PI controllers and choice of phase and gain margins. Lecture 34 will present some simulation studies on choice of start controller and phase and gain margins. Whenever we have controller design based on phase and gain margins, choice of phase and gain margins are two important things one has to take care of. One cannot arbitrarily choose phase and gain margins. So, we shall try to evolve some guidelines for choosing phase and gain margins in lecture 34. Now, some advanced level of controllers to handle plants with long dead time known as Smith predictor controllers will be discussed in the 3 lectures, lecture 35, 36 and 37. Here we shall present one advanced Smith predictor controller, which can be used for controlling stable, unstable and integrating plants. The Smith predictor controller can give us freedom to tune various controllers independently. That is one of the benefit of the advanced Smith predictor controller. Standard form based controller design will be made use of while designing the controllers of advanced Smith predictor and controller. Standard forms based controller design techniques have not drawn the attention it deserves. We shall show how simple the technique is and how standard form based controller design can give better results compared to some existing one. Then online controller of Smith predictor control structure also will be discussed, employing relay in tandem or in parallel with the controller in lecture 37. In lecture 38, we shall discuss about software and hardware implementation of PID controller and its variants. Software implementation of PID controller is relatively easy. Coming to the hardware implementation, one can have analog PID controller, digital PID controller and so on. Digital PID controllers can be effected with the help of many processors, DSP processors, FPGA and so on. Whereas, analog PID controller can be designed using field programmable analog arrays. We shall see in lecture 39 how in real time one can make use of field programmable analog arrays to design analog PID controllers. There we shall also study how that is superior to field programmable gate array based digital PID controllers. In the hardware implementation using op-amp and so, we can have various form of PID controllers. As you can see over here, a PI controller can be realized using op-amp, resistor, capacitor and resistor connected in that typical fashion. This gives us the realization, hardware realization of a PI controller, whereas the bottom one can be made use of the design of PD controller based on the op amp, resistor, capacitor and capacitor. And the way one can find the transfer function of the controllers is given over here. Yes, very easy to derive all those expressions. So, one can design PI, PD or their combinations using op amp or operational amplifiers. This is how we get in hardware the implementation of PI, PD and PID controllers. In FPAA, field programmable analog array based controller design, one has to know the structure of FPAA based controllers. So, one has to go through the modules given in the package and then design FPAA based controllers. So, here this part actually gives us the PID controller action and relay is shown over here. When relay is there are choices to design offline and online PID controllers based on the acquired plant information. Now, that is all about the content of this course, advanced control systems. In a nutshell, it can be summarized in this fashion: what we are expected to learn from this course. First of all, this course will introduce us certain classical control theory, PID controllers and their limitation, PIPD controller overcoming the structural limitations of PID controller. Then we have also the control configurations for controlling 2 input, 2 output processes, which can ultimately be extended to control of multivariable processes. Now, next we shall learn in the course what a relay control system is and how that is useful for identification of plant dynamics. Relay control using describing function analysis and using state space analysis will be studied. Next, we shall learn offline and online identification of systems, offline and online tuning of controllers. Lastly, we shall learn how to implement controllers in real life and how real time controller can be developed, how real time control systems can be developed. That is all about this course, advanced control systems.